Okay, yeah, my study was motivated by an observation that just by reading an article, the massive number of red dwarf stars, class M5 dwarf stars, and the fact that 70%, 76% of stars in our local neighborhood are red dwarfs. And I'll a picture up here, I'll show you really caught my curiosity. I'm going to basically introduce the topic, give it, explain my methodology that I used to arrive at my conclusion. Okay, we're pointing out that, when you look at a nighttime sky, most of the stars you see are bigger and brighter than the sun. However, for every star in the local neighborhood, now when I say the local neighborhood, that's increased over time. My local neighborhood is 100 parsecs, which is about 260 some light years. But for every star that is as bright or brighter than the sun, there are 10 stars that are fainter. So that in fact, we sometimes think of our sun as a small star. It really isn't. Because there are so many stars that are fainter. Okay, I drew from a star catalog called GAIA, and explain this here. This is a photometric data on stars here. It's rings in the same orientation as the Hertzsprung-Russell diagram. Down here is spectral class FGKM, and this here gives the star count per interval of 0.2 of the magnitude. And as you see, our sun is up in this area here. And they actually populations start to get rather infrequent, and it reaches a real big peak right about here. And I'm thinking somewhere here, you're starting to get to low masses to where they become failed stars. And if this curve goes on there further, that would imply that there's a huge number of lower mass bodies that we can't see. And that's my proposition for dark matter.
So that highest point here, tell me what that highest point represents.
At highest point here, actually more like right about here, I think we're starting to get failed stars. Where it fails to reach ignition temperature for, by the way, I'm working on a astrophysics test that uses the term hydrogen burning.
All right.
I remember a comment was made about that earlier. And I'm thinking this mean here could be where you're starting to get stars that fail. And what you're seeing here are brown dwarfs and stuff that, brown dwarf might burn lithium for a while. Use burning using lithium for a while, and they'll go for a while from gravitational contraction and lithium burning, but at some point they'll fade and fade away. Anyway, I'm interested in mass. And here, math alert. Here I've got to get in to how I approach the problem. I developed what I call a mass density function. Haven't seen it anywhere else. I haven't seen it anywhere else. So it's a little bit of an invention of my own. I take a small interval in there, and I add up all the star masses that are in that small mass interval, and what that creates is a mass density function. I take the ratio of it divided by the width of the mass interval, and it becomes more of a count number of stars within 100 parsecs. The interval under this curve will represent the mass of the stars between n sub A and n sub B. With that, I processed my data.
I'm not real savvy on this stuff here, so could you say that a little bit simpler so I can understand it?
Okay. All right. This is a small mass interval here, amplified a little bit.
Okay.
Okay. Of all the stars around there are stars that are going to be, some stars are going to be within this mass interval.
Okay.
Okay, you take those stars, take their masses, add them up, you come up with a number. You divide it by the width of that interval, and it becomes a dimensions quantity, which is my mass density function. And what it is, it's a dimensionless mass quantity of the total mass of all the stars in D. Like, for example, if I divide this thing up into a whole bunch of small intervals, count all the stars, add them up in each interval, and plot, and do this exercise here, you will get that mass density function.
Okay.
Okay. And jump to my result. This is the end. This is pretty much the same data, but now it's in masses. It's the mass density function of stars within 100 parsecs. Again, it shows a very steep rise, reaches this mean here, and then it will drop off into the brown dwarfs. And my conjecture is that this curve continues to rise up here. There'd be a lot of area here not represented by visible. Your observable visible matter would be the area under this curve here. And that would be most of the visible matter within 100 parsecs. There'd be a few giant stars and a few white dwarfs not in that. But that would be most of your visible matter in there. And the non-visible matter that could be in the form of rogue planets and failed stars could represent a significant amount of area over here.
So just to make sure, again, a little slow stuff here. So at the bottom it says star mass and solar mass. So one represents our sun. Our sun is our solar mass.
Our sun would be right here.
So you're saying anything that is smaller or is less mass than the sun, even 8/10 or 6/10 or 4/10, that's what's
Yeah.
right. Okay.
That's correct.
And I thought that stars, my limited knowledge, I thought that in order to become a star, that that body had to have a mass of about 4/10 of the solar mass.
Actually, the number is 0.08. And
0.08?
yeah,
Oh my God.
and someone who catch that, congratulations. This is a big problem that I'm working at here. As you see, you're seeing here, there's about 3/10 of the solar mass.
Yeah.
And I'm going to get into that more. And I have some very technical slides to show that there's a problem here. It's the very same theory that predicts 0.08 masses. Do that. Take this luminosity and use that mass luminosity relationship. This mean here is at 0.08.
So you're saying at 8% of the mass of the sun,
Yeah,
there is still enough
that's
gravity for hydrogen to fuse and become helium.
that's correct.
Wow. Okay.
That's correct. But that's a problem right now. I'm going to get more into that in a little bit, because there are other mass luminosity relationships, and I'm going to get into that that I use here to get what actually turned out to be almost about 3/10 of the solar mass.
Just to make sure I'm reading this right. So add the solar mass density equal to our star, which would be 1, right?
That's where our star would be on in that graph if it was there.
Within our neighborhood of 100 parsecs, there would be roughly, so there's 8,000 stars with our
There's
solar mass. I mean, is that kind of
80,000 solar masses.
solar mass, stars of our solar mass?
Of our solar mass. So they say solar mass above the mass of the sun.
Right.
So are we saying that, the, main sequence, is that what you're plotting here?
No, this is the population or mass population as far as. It is oriented in a familiar way on the way Hertzsprung Russell diagram and normally model. I put down here, for convenience purposes, this is roughly F, G, and again, here's one solar mass, which is the kind of the high side G.
Right.
And K and M stars. Yes.
So the premise is that, with a very low mass and stars that, they're dead, they're hard to see. So essentially with our, the tail that we're seeing there doesn't necessarily represent it.
It represents objects that the satellite can see.
But there may be many more.
Yeah.
In that.
And you don't see.
Yeah,
Yes.
I've got a question. In the previous one,
I could interpret very easily because that was, brightness.
Yeah.
This one I'm having more difficulty in, are where are these mass numbers coming from? Are you looking at brightness and? looking at
Okay.
the sequence? Or
I use the photo optic data through a mass luminosity relationship to get the mass, and this becomes a cumulative mass within the 100 parsecs.
So I thought you just, so even for those things past the peak, that
There's stuff there.
between the absolute magnitude and the mass, that relationship still applies? Do you have? I guess
I'm gonna get more into that. Yeah, I'm still in the introduction.
Yeah, sorry.
I like
Yeah, I
interactive
don't
audience.
understand that right now. If you get to it, I'll be happy.
So Roger, one last question for me. So in this, within the 100 parsecs, there are no massive blue stars then, what you're saying?
No, not at all. I didn't include them in my study. I was interested in the main sequence. Yeah, I wanted main sequence stars.
Okay, so there are some that.
There are stars. Yes, there are some stars there.
Like those big stars, all right.
I think,
Presumably.
Arcturus, I think, so, yeah.
Probably drops off pretty sharply if you're left.
Yeah.
Yeah, this right here, I specifically was after main sequence stars.
Gotcha, okay. Thanks, appreciate that.
Okay, my methodology. I use the GAIA database. I use the GAIA database to draw my raw data from. It's a big star catalog. And I kind of made that back here earlier to show you that there was a learning interactive process in working with this data. And then once I had the photometric data, that's the first graphic. So I use a mass luminosity relationship to arrive at my result. The GAIA mission is a European Space Agency satellite doing for mapping stars for star catalogs. It is out there with the L2 Earth-Sun Lagrange point, and it measures the parameters of many stars over a long period of time to produce star catalogs, and it goes from magnitude 1.6 to 21. The 21 is a big improvement over its predecessor satellites. That's what enabled me to see red dwarfs that are 100 parsecs away. The nearest red dwarf, even though they're so numerous, the nearest red dwarf, Procyon Centauri, is not even naked eye visible.
So it doesn't,
Yes.
maybe it's, I guess it's contrary to what I would have guessed. So 21 does not mean brighter, it means dimmer.
That's real
The
good.
bigger the number, the dimmer it is.
Yeah, that's correct. And I using, going out 100 parsecs, some of my data is getting down around the apparent magnitude is around 19. From this, I'll make a point about the upper end, 1.6. It does not include the bright stars of nighttime sky. This star catalog. For example, Alpha Centauri A and B are not there, but Procyon Centauri is. Sirius is not there, but the pup star is. Okay, from this, I drew a number of parameters. It has a lot of parameters. It's got proper motion, got a whole bunch of really good stuff. But for the purpose of this study, parallax, because I wanted to constrain my data collection to 100 parsecs. And it had what they call, I call it the green photometer, as well here with their analog to visual light photometer, and it measures, it reports magnitude that is similar to apparent magnitude, a little different. I'm going to get into that, a little bit of difference. There's a color index, which is their blue pass band minus their red pass band, or BP_RP. It's a color index, comparable to B minus D of stars. And during the process of my searching, I used the derived parameter, from the parallax to get an absolute magnitude and the GAIA photometry scale. Okay, and there's a lot of places here I had to make comparisons of GAIA data with known stars. And with that, I also drew right-Simpson declination for purposes of matching them up.
So this whole section is on just apparent magnitude, all of this.
Okay, the GAIA reports apparent magnitude only,
Okay.
but it also reports parallax.
Okay.
So, with apparent magnitude and parallax, you can derive the absolute magnitude.
And parallax helps you derive the distance, right?
It's for distance, yes.
For distance, right?
Okay. Explain to the guy photometry. This is a spectrum, 300 nanometers, which is into the ultraviolet, 1100 nanometers, which is low to the infrared. I throw in the visible spectrum here for reference purposes. The pass bands for the GAIA photometry much wider than the visible band. Well, it's in low to the infrared, and it's two pass bands, the blue and the red, for presenting a color index. And you might look at this here because the sensitivity reaching into the infrared, that redder stars would appear a little brighter in the GAIA photometer, and they do. And to quantify that,
It just kind of show me the beginning, the end of the visible.
okay, here's the violet end, the
Okay.
visible, and here's the red end of the visible.
I got you.
Yeah, red comes out just about pretty much about 700 nanometers. Those-
Red melts apart.
Mhm. And the GAIA photometer reaches a little bit beyond on both extremes. Okay, what I did here is I compared two different ways the GAIA photometry with traditional photometry. And again, here's where the right ascension and declination and identifying known stars and making comparisons is done. I plotted the FC color index. With color index around zero is there. And color indexes through here round up very red stars. This is the photometric difference between the traditional and the GAIA photometry. And as you can see, with the redder stars, that difference goes greater and greater. And the numbers out of the GAIA are higher. And I did the same thing with absolute magnitude, and again, a photometric difference. And that was produced a relationship that was easier to use and making quick conversions.
And the purpose of this is what?
The purpose of this is understanding when the GAIA photometry gave a magnitude of 12, what is it really? What is it in a more familiar magnitude?
Okay.
And in the case of 12, the number of 12 I threw out, the GAIA photometry would be measuring around 10. So it's a little brighter. Okay, I did this just with as an exercise to take a closer look at their color index. There's the blue pass band minus the red pass band, and compared with B minus D. Again, blue white descent, red descent.
So what did this tell us?
Basically, I did this just for this illustrative purpose. I used BPRP in my data draws. But it doesn't have a real direct connection to my work. And I'm going to explain that in a couple slides.
Given that the brightness from the GAIA and traditional methods are different, what if you're trying to if you're calculating mass, you're going to get a different mass number from one or the other. So which
Okay, there's two things going on here.
Yeah.
The difference of what we think of as normal photometry, visible light photometry compared to GAIA photometry. I need to understand and deal with that difference to work accurately. A lot of the textbooks and the resources that you pull up in astrophysics always work, and usually the visible and some of the infrared bands that are often there. And so, I had to understand the difference. So, I'm calibrating. That's probably the best way to put it. Okay, the data draw. This is illustrative purposes only. I really need to work this out more and more details. But basically, you look at the Hertzsprung-Russell diagram, which this is what this is here. I had two filters, or four filters total. Filter to get anything dimmer than about an absolute magnitude 3.5. And anything, and I want to cut off at 12.6, which that is 12.6 actually is a GAIA number, which corresponds to roughly 14.5 in regular visible magnitude. In terms of, absolute magnitude. Also, I had two other filters represented by these two lines here. One of them to eliminate stars, this is here to eliminate the white dwarfs, and the one here to eliminate giant stars.
So for the absolute magnitude of 3.5, can you just give me a reference of a familiar star that I might see that is about 3.5?
Absolute magnitude?
Yeah.
I'm hard pressed. I can't really name a star. I could go pull up my spreadsheets and find one.
Oh, okay. But, when we're talking about things like Vega, well, Vega is very bright. It's not 3.5.
Yeah, it's a lot wider than that. They, obviously, what my remark earlier, those brighter stars are not in this. Then the sun isn't either.
But I could see a 3.5 with my naked eye, right?
Oh, yeah,
But not a 12.6.
no.
Those are absolute magnitudes, not.
Depends on the
There's two things. In terms of what you see in the sky, is that, you understand, in a very good dark night, you can see, parent magnitudes of about 6.
Okay.
And, a more normal viewing conditions, only 5, maybe towards 4 in Charlottesville.
So 10 parsecs out, absolute magnitude and apparent magnitude
All the same.
are the same. But if a star is twice as close, it's going to be 4 times brighter, which is about a magnitude and a half or so.
Okay.
So, a star that's, 5 parsecs away, its apparent magnitude is going to be 1.5 amount more than or less than its absolute. So, a Big Dipper star is, I think, probably in 2 apparent magnitudes, something like that. So if those stars were about, kind of trying to do the math here in my head.
And one thing that's easy to remember is that 2.5 magnitudes is an order of magnitude.
Yeah.
And a factor of 100 is 5 magnitudes.
Yeah, and the sun, I think the sun is absolute magnitude, but like.
27, minus 27. I believe.
No, absolute.
Oh, absolute magnitude is about 4.5.
4.5, right? So.
So the little that I know about what you have on the chart there, though, is so those white dwarfs there, those
They're filtered out.
filtered up there, and they would be very, very dim anyway, right?
Actually, we can pick up a bunch of them
You get it, okay.
in the star catalog.
And up at the very top up there, that's the bright giant super giants, the bigger.
That's correct.
Big blue ones.
Big blue ones and big red ones.
Yeah.
Big blue ones, pretty, get eliminated. They're just so white.
Okay, guys.
So why are you filtering out white dwarfs and giants? Is that because
Because I'm after main sequence stars.
is that because they're gonna screw up your luminosity? Function?
Kind of, yes. Yeah, they will obey the, these mass-luminosity relationships apply only to main sequence stars.
I see, okay, that's fine.
So yeah, that's my motive for eliminating them.
Mhm.
And they're a comparatively small number anyhow. Okay. And I might point out, I got about 250,000 stars in this data draw. Which over earlier attempts, for example, the Hipparchus satellite, which is an earlier satellite comparable to Gaia, but it's about 10 years older, could only reach out to a magnitude, apparent magnitude of about 14, which means 10 parsecs is about the furthest you can see out and see really faint stars, like less M5 dwarfs. This one here, this sensitivity here allowed me to go out a whole lot further, out to 100 parsecs. Again, this is the draw. This is the same thing that you saw earlier. It gives a star count per interval of 0.2 of magnitude over the range of absolute magnitudes. And again, this is Gaia photometry. So this 12 here would be like 14, about 14 and a half, you know, in traditional visible light photometry. Yeah, went the wrong way. Okay, mass-luminosity. What I use is a method first published by Delfosse, et cetera, et al., where they used orbital parameters in stars and binary systems to try to directly measure the mass. And if you think of two stars orbiting each other, more massive, that could be doing this, less massive, doing that. And by doing that, you can come up with, Delfosse claims he was able to get, he used stars with a 10% precision. You know, 10% or better precision. And I took his star set, added some more to it, researched out and got new estimates for a little updated from the ones that Delfosse had, and ran and did much the same thing. And this is where it lies. And it was basically this. No, that's the wrong way here. Oh no, that's going the right way. And this is my mass-luminosity relationship here of the stars. I got like 50 stars in there, and I did, you know, an empirical curve to, you know, to produce my mass-luminosity relationship.
And they did this with binary stars because they were passing
They-
in front and back of each other and
Actually,
calculating that mass.
there are a lot of ways of doing that, but if you know, okay, this way, Doppler effects you can have with how fast it's coming towards you. And if it's a visible binary, you know, which a lot of them are, you know how far the stars are apart. And from that, you can get how big the orbit is, how fast they're moved by it, and how fast they're moving in the size of the orbit.
Right.
You can calculate the mass of both stars. And so it's a more or less a direct comparison. Well, a lot of the theoretical mass luminosity relationships, you know, come out of theory. And that's a problem I'm right now still dealing with, trying to understand why the big difference, because these empirical mass luminosity relationships produce masses that are about 3 times greater. And for the very faint class and 5 dwarfs.
It would seem like it would be apparent fast. Well, so how do you discover, is it the Doppler effect to get the
The
size?
Doppler will give you the speed that it probably
Okay, speed, okay.
And by observing binary thing, you can get a plot of the orbit of that star. And by how fast they're moving,
Right,
you
it's
see
how close they are.
by how close they're, if they're real close versus further away. But you work that out, you know, with the orbital mechanics, so that you know you get that you can back out the mass of both stars. And to me, that was a direct way of making the measurement. And that's sort of why I went with it here. Yes.
So, but you don't have, not all of the stars you're observing are binary, so you're using this, the subset that aren't binaries, again, is another form of calibration to get that mass.
I said, calibrating mass luminosity, that's all I'm
And
doing,
then you can apply that
to my 250,000 stars. And that's what I did. Okay, let's back into the final result. I'm thinking that there's a possibility that this curve extends upward, and that there's a lot of matter in here we're not observing. And if you look at the area under the curve, that's a substantial amount of area, you know, the area of stuff that could be out there that you can't observe over what you can observe, which is the area under this curve. Okay, that basically includes the body of my briefing. I have more slides to get very technical. And it's dealing with this mass luminosity problem. I can go through them if there's interest here for me to do that. Yes.
So just to get a protocol, at least for me, and I'm sure that we might find this to be a little overhead, but so how would they determine the mass of our sun, as an example? How do you determine the mass of our sun? Is that a relatively simple
I haven't gone through the, the physics of doing it myself,
Okay,
but, how fast the Earth goes around the sun is a very good indicator, because, how fast the Earth is going around the sun, you can determine the force of gravity that is acting on our sun, on our Earth from the sun. And, okay, you can think of it real quickly, centrifugal force.
yeah,
That's trying to pull Earth away from the sun.
Yeah.
And because gravity is balanced against that centrifugal force, to keep the Earth going around the sun. Okay, if at that point, you can calculate centrifugal force to get how much gravity is interacting on that, and just simply your simple gravitation equation, gravity mass equation, you can back out the mass of the sun.
okay. And then just because you're aspect up there, so I'm always trying to understand, well, I guess everybody is, but what is dark matter? What is it? I want to see something. So if you use those failed stars and rogue planets as dark matter, that is nowhere near going to get us the mass that we need.
I don't know. The area of that curve, this curve could be going exponential up there, which means this area already is a substantial amount of area here, maybe not quite enough, but a substantial amount of area compared to the area under this curve, which represents the observable area.
So in my mind, he's saying that you've got a mass of physical stuff that failed to ignite and make a star. So therefore it's not visible to us in visible light. So that is a lump of a lot of mass compared to what the theory of dark matter is, which is.
There is no theory.
Yeah.
Right. So you've got a lump of mass, concentrated mass, that's gonna represent a lot of dust.
Right.
That would be dark matter. So this could very well account for
A good part of it.
a whole lot more of the dark matter mass than what the.
That's real quick. Is everybody here familiar with the dark matter issue?
Not everybody.
Go ahead, go ahead.
I'll give a little bit of a primer on it. There are two compelling arguments for the existence of dark matter. One argument are models people run of galaxies. If you take all observable matter, put them in there, gravitationally interact with stuff, the galaxy flies apart. You postulate a dark matter in there that would give more gravitational attraction. The models work. The second compelling argument is gravitational lensing. If you have a foreground galaxy and images of background galaxies that are distorted by gravitational lensing, from the gravitational lensing effect, you can back out what that galaxy must weigh. And that turns out to be a whole lot heavier than the amount of visible matter that you can account for. Those are the two compelling arguments for dark matter.
Go down a little different avenue. We can see protoplanetary disks. We actually see systems forming. Are we seeing any tiny yes, things that are substantially smaller in mass that could conceivably form objects?
Once in a while, there are a couple of planets in the exoplanet catalog that are rogue planets.
Yeah.
There are some of them there, but they're hard to spot.
And I've seen a lot of modeling of in that phase where you are forming planets and it's kind of you're banging into each other and all that.
Yeah.
If you're gonna get a substantial amount of mass injected,
I think so.
and, but.
I think the early solar system had probably had a lot more matter in the disk than it does today. And here's another one. Consider the hot Jupiter problem. One of the leading theories is that a big planet formed out distance and migrated in. Where did that angular momentum of its orbit go?
Yeah.
The only thing I can come up with ejecting other stuff. I did it. One of my fun calculations I did is I calculated how far Jupiter migrate inward if it ejected all 7 other planets. And it was still outside the orbit of Mars.
So have you, did you look at the mass that would be required to in your calculations to compensate or to account for the dark matter that's calculated. So if you're saying, you know, if there's that area, what type of numbers are you looking at?
Actually here, going beyond this point here, I don't have much to go on. I really don't. I have a, strong suspicion, and until I resolve this 08 thing here, if I get that resolved and I have a clear indication that this is the start of the fatal points, I have a very, very good argument for the dark matter.
So Roger, you said that the reason why we know there has to be dark matter is that the galaxy, unless you had more matter, the galaxy would just fly apart.
That's the computer simulation side of it.
Right. So how much more matter would we need? Is it like twice as much matter that's in the galaxy now, 10 times more, 100 times more?
About 5 times more, somewhere around there, and someone might have it.
It varies
Remember.
from galaxy.
Mhm.
They have to,
Okay.
numbers required. So it's a density issue.
I mean, hearing that, to me, that only kind of makes sense. That you've got 5 times as much, or approximately, 5 times the stuff that's not as bright that you can see as the stuff you can see. That's not too far fetched.
But the problem is, at least my limited reading on this stuff here, is you would think that there'd be a lot more theories, kind of like this, to say, oh, so here, you don't hear people say, oh, we think that it might be X or Y. It's just like, this is the first I've heard that might be some proof that there is dark matter, and it might be that those failed stars on your planet.
The other avenue that some people are going down with spectral dark matter is that are modeled gravity. But there's also some evidence that suggests it's not. So, but there are because we've never been able to find this stuff.
Yeah.
You can't find a particle to see the word. It's still an open question.
It's a really open question, Sue.
Yeah.
It's just one possible answer. Yeah, I see a lot of hands up. I'll start here.
So why do you think someone else hasn't postulated this before? Because what you're saying is,
I haven't heard it.
okay, it seems like it's fairly straightforward that there's a lot of things out there that
We can't see.
that have an ignited versus, more exotic forms of matter.
When,
Of course, matter is maybe more exciting, but. Wins.
I've heard some, at UVA of autism, some, of course, so there's some of what you're saying is going on. Well, I've got a really crazy idea I want to pass. That dark matter has gravity.
that's the only property, that's the only property that we can detect. So dark matter.
So what I was wondering about the failing stars, not just a chemical thing going on, but maybe the black matter's gravity is having some effect on the deterioration of the star. What do you think?
Okay, well, the idea here is that, okay, if failed stars and rogue planets is the dark matter, we don't see it out there, but it's still gravitating.
Huh.
As you know, I'm standing on a very dark piece of body right now. And it's gravity that's holding me here. As all everyone here. Yes,
So 2 questions, actually. The first is, I'm still not quite getting, objects, well, I'll say, that are between 0.1 and let's say 0.3 solar masses on your graph there. They show, do stellar models say that anything of that size in a body is going to ignite as a star? Or are you saying that there are objects of that size that aren't igniting as stars?
because I don't think anything's going to ignite. Except possibly lithium.
So then I don't understand
Why you see
how those dots even exist, because how do we see them? Why do they shine?
under gravitational contraction, they'll glow for a while.
So
you
these
know,
are,
they
these
coalesce.
are very new things,
They'd be new things
very new things, okay.
and short-lived. And the short-lived may, account for the fact that they tail
Okay,
off.
so all those things, yeah, so. Stellar burning isn't it burning below 0.3 or whatever?
Goes out here.
Okay, so that's the first question. The second question is, when people talk about dark matter and how it impacts the velocities of stars orbiting galaxies, let's say, I thought there's a presumption of a particular distribution of that matter in space. And yes,
They speculated.
yeah,
And they speculate, and I've seen speculations that it's within the galactic disk. That would fit very well with this.
yeah.
Another one, there's this big blob of distributed dark matter over, outside the galaxy as well.
So,
This would probably not help too much there.
yeah, that's where I was going, is what does that, when you do it this way, does this imply a particular distribution of this sort of matter?
It does.
Explain those observations.
It does. It provides that the dark matter is in amongst the other stars.
Okay.
One thing that is confusing when you look at a number of different galaxies is that you seem to have different quantities and distribution of dark matter required to keep them in balance.
Yeah.
And it varies. It's not like there's a single, it's almost like you have two separate each
I
galaxy.
think,
And that's very,
the galactic models, when they did it, they put distributions in there and found that they could make the model work. And I'm not sure exactly, I haven't studied that work in detail, to know exactly how they did that. There was a question way back there.
Where does WIMPs come into this?
A WIMP is a conjectured dark matter particle. It stands for weakly interactive massive particle. And it's a postulated particle. They're building multi-billion-dollar detectors in the South Pole to try to detect an interaction that they could attribute to a WIMP. They're really looking hard for them, but so far, no luck.
I think the other thing to know is that of all the mass that's postulated to be in the universe, or whatever you might call it, we can only account for what 4.5% of mass.
I think it may also be including,
Visible mass.
it may also be including, what they call dark energy.
Right, there's dark energy, dark mass, and then visible mass. So
Mhm.
I can only imagine if you're talking about some kind of matter that actually is matter I think it is, you're possibly gonna guess that there's gotta be if we can only see 4.5%, that means another maybe 40% of that's dark matter, being the rest being dark energy.
That's the,
And that's a lot of stuff that we can't see. And also, if you look at your galaxy clusters, the huge galaxy clusters that we have, it's postulated that they could not be held together unless there was more mass than what's seen in the galaxies themselves. So dark matter exists throughout the surrounding area of the galactic clusters. That's how would that kind of stuff that you're debating here get out there?
it may not be out there.
Well, something is holding this huge amount of matter in the form of galaxies that are flying at massive speeds that they would break apart, but they're being held together. So it's postulated that dark matter is surrounding this and keeps these.
I don't know the answer to that, but sure. I don't know if the mutual gravitation between the galaxies is enough or not. I really don't know the answer to that.
Postulated that it's not.
Well, but the universe is always expanding. So how do you think this dark matter thinning out? What's?
Depending on what dark matter proves to be, the dark matter would be following the because the exploits of regular matter, just alongside of it.
That would be, very, dark energy coming.
Dark energy is even more mysterious. I've read some articles giving compelling arguments, but it's a while ago that I actually read them for its existence. But my first impression of dark energy is it's misnamed. It's not a form of energy that can harness in the future for powering our starships. But it's because the existence of dark energy is postulated as a sort of anti-gravity that accounts for the fact that the expansion of the universe is accelerating.
I don't know if we want to harness it for starships. There's planets out there, more likely to.
So I've got a question here. I'm trying to think about how you would take this from conjecture into some sort of hypothesis. That's about the only way that I could see that we could do that is some sort of simulation that would give rise to these dark things, because what you're suggesting, go ahead.
Yeah, I think we're gonna get a good wave real soon that might turn this from a conjecture to fact. And we are occasionally getting rogue planets and other objects, detecting them mostly through microlensing stars. Eventually, that database will flesh out to where you might have good enough statistics, compare, okay, what would it take to produce a microlensing event? And what's the likelihood that we get it? And from that, you may be able to back out how many objects are out there.
So who's doing these microlens? I mean, what is?
I only read about it because I read it, I was reading articles about exoplanet discoveries.
Recently, James Webb directly imaged some rogue billion size planets, I think, in the star forming region in light also. There were a number of bigger size.
Well, I mean,
Some of those may be warm enough to actually be detected.
even micro, I mean, you're trying to look for things that are relatively small. I mean, first of all, just kind of basis on this thing here. If I read that graph right, the total matter and the total amount of mass within this 100 parsec bubble of stars between 0.8 and 1 solar masses is about, I'd say, half of the amount of matter that's between 0.2 and 0.4. Is that how you should read this graph?
The way to read the graph is the mass of the stars, say from this mass to this mass, will be represented by the area under the curve.
Yeah, so that's what I'm saying. The area, think about from some 0.8 to 1, that area under the curve is a mass fraction of the total.
Of visible stuff at that max size.
And so from 0.2 to 0.4, it's about twice that.
Mhm.
Okay. And you're suggesting that, presumably some sort of power law that says there's lots of tiny, the number of tiny things.
That's pretty conjectorial.
Yeah.
Conjectorial, but it's plausible.
It's plausible, yeah, but all that stuff is not seen, and then, it gets back to how possible detecting it.
So Dave, good question. So remember Dr. Lee was here, 2 months ago? She said they kind of identified 5,000 exoplanets, right?
Most of them around stars though.
Yeah. How does that fit into this? Because she said there's not very many very large exoplanets like Jupiter.
Yeah, I mean, that's just suggesting that in general, that's kind of like a power law. There are more small things than there are large things, just kind of in general.
And this conjecture is many more small things.
But yeah, this thing here, since it's the area under the curve, small things have less mass, so there have to be
More of them.
many more of them to have total mass more than the large things.
One thing maybe that might work is if you're looking again at the planetary system we see forming, and how much of the matter in that disk ends up in the star, how much of it ends up in planetary bodies, and if we have an ability to look at you know, see them at different stages, maybe we can get a sense of how much of the original matter ends up being ejected.
Ejected
And
out.
that would give you some kind of a handle on how much stuff there must be out there between.
That would be, I tend to suspect that it would not be too terribly reliable. I think of the biggest hope on it, if we, over time, we're gonna get more and more rogue planets and, and some data on them.
Hopefully not acid drops.
Oh, some of them might become spectacular comets.
You know, if there are any instrumentation under development that will give you more data to go on?
I don't know if there's a successor to the Gaia mission, which is the primary source of my data.
So you said you ignored the really big stuff. Is it fair to say that, in terms of the total mass contribution of big stuff, it is much smaller than the mass on here?
I think it is,
Okay.
because those stars are few in number.
So then the other thing you said is, I think you suggested that, this is another, I guess, the ratio between dark matter and visible matter, which is the area under this curve, basically, right?
Yes.
Is a factor of 10 or 9 or something.
I'd say the area under this curve here would represent about at least 90% of the visible matter.
Okay.
Yeah.
So in the
It's not
dark,
the,
okay, but so it was most of the visible matter, and the dark matter is about 10 times that.
because these deal with the most common stars in our galaxy.
Yeah. No, I'm saying the dark matter. So I'm just trying to visualize what this curve is going to look like, because this curve, if this is the curve, you know, where your red line goes up, and it replaces all of dark matter, then the area under the curve has got to be about 9 or 10 times what this is showing.
And for total counting, but I'd say about 5 times.
Okay, 5 times. Okay, so that's, I mean, drawing the red line really way up. It really is got to go way up, because
Yes.
you know, you don't have much.
Yeah, that line was just stuck there. There's no extrapolation function that I use to create
Yeah,
it.
it's got to go up. It's got to go up and get back to 0, 0. And the total area under the curve has got to be ordered.
Getting back to 0, 0 might be a proton.
Yeah.
Yes.
What about, looking at the mass in the, like the Oort cloud and whatnots, and maybe comparing that to other known solar systems? Because you have to assume that it would be.
Are you aware? I don't know, but are there mass estimates of what the Oort cloud weighs?
That was a question I was going to think of, that I was thinking about. I'm not aware of, what is the estimated amount of mass that's out there in the Kuiper Belt and all that. I don't think I've ever seen how much mass is out there compared to what's in the sun. I think it would be,
I don't know.
There's no way to know it because there's no known mechanism that discharges comets from the Oort cloud in your solar system. If you don't know what that mechanism is, you can't estimate it.
Roger, I'm going to do a quick check and see if there's anybody online with questions. Although I'm not going to be able to figure that out, so just stay right here. Let me see if I can find anything. Jim Brown is still online. Any questions out there?
No, not for me, but thanks very much for asking.
All right, that's another question. Anybody else in here? We good? Yeah, absolutely. So for our speakers, you remember too, but for our speakers, we do have the covenant caffeine and a coffee now that we sent to you and free support as well. So thanks so much. That was good. I think one last question. I thought you were not